I haven't said anything down, so can you hear me now? Yeah, I haven't said anything before, so that's why. Seems like folks being late today a little bit. So let's give it, 1 more minute before we start. Okay, let's begin. So good morning. Do you have any questions before we get started? Okay, no question. So let's revisit what we did last time. So last time we were discussing, right, the idea of an Ito process and Ito formula. Okay, so Ito process is anything, right, any stochastic process within some given filtration. So you may think that the filtration is generated by the Bragg motion. So in other words, everything here is controlled by the Bragg motion in terms of information. But right, just because this process is knowable, okay, by the Bragg motion up to time t, doesn't mean it has to be, something like this, right? So try to think of the idea of information, all right, information flow. Something is knowable by the Bragg motion up to time t. You may think that is something like this. Okay, so for example, the stochastic process is e to the t plus wt. That's correct, right? I mean, that's fine. This is part of this is an example of a process that is knowable by the Bragg motion up to time t. But notice that when you do this, you're thinking of a Markov process. Okay. I suppose that we have heard of the word Markov before. Is this a new word for anyone? I mean, you don't have to know precisely what it is, but you should have heard of it, right? Yeah. So basically, Markov, you kind of think of Markov as only depending on the most recent information, or only depending on the present, and not path dependent. So Markov actually in the world of option would correspond to European option, okay? Because you see, yes, right, when we say this, notice this notation doesn't mean only Bragg motion up at time t, but it includes the whole past history, right? This includes basically wt, ws between 0 and t, right? It does not just include point t. So of course, when you do this, it's fine. Is an example, right, of something that's in the filtration, the Bragg motion, but that is, not general enough, right? In the world of option, or in just the world of process in general, you can think of a path-dependent object. So that's why, right, we think of something like this. As I guess one of the, again, it's not most general yet, but it's more general than this, right? It's general in terms of like a process that is in the Brownian motion filtration, right? What's the difference between this one and this one? You see clearly this one is path dependent, right? Path dependent. Not Markov. Okay, because to be able to construct or know, right, this process at time t, you need to use the whole history of the Brown motion, right, on from 0 to t. And by the way, right, of course, when we do this, the alpha and the beta must be also adapted to the Brownian motion filtration. So in other words, right, alpha t is in this, and beta t is also in this. An example, right, would be what you saw in your homework of last week. Sorry, this is ds, right? ds. And this is dws. I mean, I happen to choose alpha and beta to be the same. They don't have to be, okay? But the point is, right, notice that when we write something like this, it makes complete sense mathematically, but we don't necessarily have a formula in this way, right? We don't have a closed form formula of xt as a function of only t and wt. Well, why not? Well, the why not is very simple, because it's strictly path dependent, right? Strictly path dependent. That is, you know, if you can convert xt into this form, somehow you're saying, yeah, it looks like it's path dependent. It's really a Brown motion. Sorry, it's really Markov. You understand? So, right, the point being is that these two, right, the point of considering an Ito process. So this is an Ito process right here, right? It's an Ito process. Right. I mean, clearly this is also an Ito process. It's not like it's not an Ito process, but the notion of Ito process, right, extends the idea of how a process depends on Brown motion to the whole history of it. Is that okay? So let me see, right? There are many things to say here to give you an idea of how these things, how these pieces are put together. So I'm just trying to see what's the best way to say it. So, right. So going back to, right, the idea of, you know, just because something is a Markov process, right, doesn't mean that it cannot be expressed as a integral, okay, as a past history. So in other words, right, the whole point of, like, for example, Ito's formula in the easy way, that is, you know, let's take a look at this, right? We have d e to the t plus wt, right? We discussed is going to be e to the t plus wt dt plus e to the t plus wt dwt, right? Plus 1/2 e to the t plus wt dt again, right? Where this comes from the formula, right? d of f twt is f sub t dt plus f sub x dwt plus 1/2 f sub xx dt. Okay. What this means, right? What this means is e to the t plus wt can be written as an integral, right? From 0 to t, for example, is 1 plus e to the s plus ws, right? I guess somehow, right, this and this together make it 3/2. And then like that. Is that okay? So this is writing it as an integral. But of course, right, there's a simpler way to write it, right? Namely this, right? Namely this. So this has a Markov representation. On the other hand, right, again, like I said, something like this does not have a Markov representation because does not necessarily have a Markov representation because you cannot have a closed form uh, formula for some other structure like this. So the connection with classical calculus is just basically the class of differentiable function. So the idea there, right, if you remember, is that you could basically write many things as an integral. For example, right, let's say t squared is the integral from 0 to t of 2s ds, right, for example. So t squared is an integral from 0 to t of something ds. But of course, t squared itself, right, is a function at t. On the other hand, you could take some weird function like e to the minus s squared over 2, and you can call that, right, some f of t. Yes, the point is that you don't have a closed form solution of f of t. But that doesn't mean that you do not, right, look at this as a non-differentiable function. F of t right here, right, being something like the CDF, right? If you throw in, let's say, 1 over square root 2 pi, then it becomes like the CDF, right, of a normal, standard normal, right? The fact that you cannot write it as a closed form formula doesn't prevent you from not considering it as a differentiable function, right? So same thing here. Sometimes we have a closed form representation of some process. That's good. If not, right, considering it as a Ito process, meaning knowing how to get, right, how to reconstruct it from some dt integral and dwt integral, it is perfectly legit, and we can work with that, right? Same thing here, for example, let's say you have a function like this, right? Suppose I have a function like this. You definitely, you should have seen, right? For example, if I have this function square and I differentiate it, this is a calculus question, right? That can be is a valid calculus question, and you can assign it to a calculus student. Do you agree? If I were to ask you to differentiate this function square, you should be able to do it, right? What is the derivative of this function square, for example?
Isn't that just basically the function inside that integral?
Sorry, Don, I can't hear you. What do you say?
Hold on. Isn't the derivative of ft just basically that function in the integral?
Yeah, but I'm differentiating not ft, right? I'm differentiating f squared. Right?
Oh, that's right.
I'm differentiating a function of, right? So that's why. Or, right?
Okay.
Or I'm differentiating e to ft if I feel like it, right? So
Oh, I see.
what is
Okay.
it?
Should we use the chain rule?
Yeah, exactly, right? It's just a chain rule. So in other words, this is going to be, right, the first question will be, right, 2ft times f prime of t, where now, right, what Don said is correct. In other words, 2ft 1 over square root of 2 pi e to minus t squared over 2. Yes. And the second one, right, will be, right, like Johan said, first just differentiate this, use a chain rule. Then, right, it's going to be this times this. Yes. But do you realize that there's another way to write this in the Ito formula formulation, right? Here, again, let me write back for you, right? ft is this. You see that, first of all, this means dft is this dt, right? That's actually what Don was just saying about derivative. But instead of writing derivative, I write like this in the Ito formulation. But that's fine, right? It's the same thing. In other words, this is like an Ito process with this being alpha t and beta t equal to 0, right? And then when I ask this, this is nothing but asking df square of t. Well, apply Ito's formula, right? It's going to be 2ft, right? Well, so here, right? Yeah, so just basically differentiate this with respect to t. So 2ft dt, because there's no boundary motion component. So that's Ito's formula, right? But of course, it's 2ft dt is, sorry, what am I saying, right? Is 2ft dft, sorry. Not 2ft dt, sorry. 2ft dft, right? So that exactly is 2ft times this. Which is exactly, right, the chain rule. So d, right, e to the ft is, right, e to the ft dft, which is exactly this guy right here. All right. So all I was doing is, instead of writing dt on this side, right, instead of writing dt on this side, I divide by dt on the other side, right? So the classical calculus rule, you kind of look at this as an operator, d over dt. The Ito kind of formulation kind of asks you to write the differential of the function and the dt on the other side, okay? But what I'm trying to say is Ito's formula by itself, right? So Ito's formula says this, right? Suppose you have dxt is alpha t dt plus sigma plus beta t dwt, then df, right, of txt is f sub t dt plus f sub x dxt plus 1/2 f sub xx quadratic variation. Okay, so actually before what I was saying was wrong, right? When I do this, what I should differentiate is with respect to x, right? Where x here is being the f, right? X here plays a role of f. This is the f here plays a role of x, right? So actually there was no t component, right? I was wrong there, but it was just the x component, you see? And the quadratic variation of x, because because here there's no boundary motion component, the quadratic component is also 0. Okay. But the point I want to make is that Ito's formula, right, is an extension of the chain rule. That's all. An Ito process is an extension of the classical differentiable function. All right. So I'll leave it like that. Okay, I'll leave it like that. So in other words, that I just want to make more sense out of what we did, before in the classical context, to show you why, right, we care about this. Is because basically, why is calculus important, right? Calculus is important because basically you study function in time in some way, right? Like think of your differential equation classes. You look at models of processes in time, and most of this model you assume are differentiable, and you model the derivatives, right? So here right? In math finance or in stochastic modeling, you also model the derivative, right? But instead of derivative, here you model the differential of the process itself, and you split it in terms of a dt term and a noise term, okay? And then you work with it. So just like, right, just like there is, right, there are non-differentiable functions in calculus, right? There's also non-Ito process. There are process that is in the filtration of the Brownian motion, but is not Ito process. Okay. So the classical example I want to give is the xt, which is equal to the max of the Brownian motion. Okay. Now, this I would admit that it's not easy to see why this is not an Ito process. Okay. In other words, when you take the maximum of the Brownian motion from time 0 to time t, I claim that you cannot decompose it into, there's no such thing like this. You cannot find alpha and beta that will do so. All right. It is not straightforward. Okay. This is why like something like stochastic analysis, which is, studying deeper the aspect of stochastic calculus is important, because it explains why this cannot happen. I don't think I want to go as deep, right, into that aspect. I mean, we will kind of refer to this later on, because this is connected with the look back option, okay? The look back option, because you have to take the max of the whole path of the stock, which somehow is related to the max of the Brownian motion. So the difficulty there exactly is, okay, the maximum of the Brownian motion on the whole path cannot be written, as a Ito process, as a dt integral and a dwt integral. So, but again, right, the structure of the Ito process, while we have it, is very valuable for us to write down the math, to write down the model, and to see how the pieces fit together. All right, so now that's the math right there. Any question on this? All right. So now let's go back to the finance a little bit, okay? So in terms of the finance, the use of Ito's formula, right? The use of Ito's formula, at least for us right now, right? There are many use, but so first use for us is to establish rigorously that the following three different formulations of the Black-Scholes model are equivalent. Sorry. Mu dt plus sigma dwt.
It is dst divided by st, not dst divided by dst.
Thank you, Sharon. You're perfectly right. Yes, thank you. Yes. So this is the percentage return. Right. And this is the log return. And the full model itself. Right. And so I won't go through, right, the derivation again, but I think it's a very good exercise for you to, right, first of all, see how these pieces are connected by calculus. All right. Second, try to see the meaning of each of this, right, piece of information. They each discuss a separate piece of the finance. All right. This tells you how the log return, how the percentage return behave. All right. And try to see how the DT and the WT, right, plays a role in this part. How the DT and the WT plays a role in the log return. And actually here, you should appreciate that here it's just a stock price model. I'm not sure physically there's a lot of things to see here besides a log normal distribution of the stock price. Okay, but I can tell you that right before, one thing that I do not appreciate so much is the difference between the price and the returns. Okay, but financially they are fundamentally different, right? And like I said, I try to tell you in the lecture 1 or 2, I think the returns are more fundamental in terms of finance than the price itself. People investing, right, in portfolios, technically speaking, don't care about the price, right? They care about the returns, right? You can buy something at 1 cent, and if you sell it at 5 cents, my gosh, right? You make 500% return. But if you buy something at $100 and you sell at $101, well, you only make a 1% return. So, right, I mean, that's the point. So price, of course, we do care about price because it reflects back into, like, you know, call option payoff and everything like that. But right, returns in some angle, right, from some angle is a more fundamental object. Anyway, so that's the first use. So now let's focus on the pricing angle. Okay, we have talked about it before anyway, but now let's put this on a formal, right, or rigorous mathematical foundation. Just as before, right, we use these models anyway, but without Ito's formula, right, you cannot see the connection, or you cannot establish the connection rigorously. Now let's talk about pricing, okay? Pricing of a call option of a derivative, right? So a derivative, let's right now, right, let's just look at the European style. By European, I mean a derivative, right, at time t, right, whose payoff is a function of st. That's it, right? This is in distinction with, I guess you know, right? This is in distinction with exotic, right? Derivatives, where the payoff will be a function of the entire path. So here I'm being lazy, I'm just trying this. But right, what it means is, right, this function is not the same as that function in some way, or it could be. But basically, right, you take the whole path of the stock and you do something with it. So you could integrate it, right? That will be Asian. You could take the max, that will be look back. You could look at how the boundary get crossed. That's boundary, right? That's boundary, you know, derivatives and other kinds, all right? And also, of course, there's American, right? Where American is basically, is still a function, but you are allowed a random time, right? Stopping time. I believe the professor Casper should have discussed stopping time a little bit, right? In Math Finance 1. I would be surprised if he doesn't. But anyway, right, don't worry about it. If you haven't heard, but basically you should have heard American option before, right? And I think you should have, right? And the whole idea, right, the whole difference is here, this time is a random time, right? The user, the option holder, gets to choose when they want to exercise and collect, right, this payoff. Whether here, right, the user have no choice in terms of time, right? They can only wait until big T and collect this function, right? Anyway, so we want to focus on the European first, right? And then we discuss this later. But even with European option, right, there's a lot of things to discuss already, especially the whole idea of risk neutral pricing framework, right? In other words, you say something like this, right? Basically, remember, so now let's go back to our stock model, right? And let me use the classical way of writing it. So now I put ST on this side, okay? And notice that we haven't really get into it yet, but because I write mu here, all right, I write mu here, this is a physical model. Okay, what is physical about it? The physical model about it is like this, right? Because this is equivalent to saying that stock price is like this. Right. And a consequence of this formula is that if I take expectation, right, no tilde, because this is W, right, physical model, I look at the discounted, right, this is not S0, right? In fact, it's going to be equal to, what was it? E to the mu minus R, right, times T. And so S0, right, which is not S0. If mu is not equal to R, right? Which we assume that that doesn't have to be the case. Okay, so that's why we say it's a physical model. But so let's just wonder why we want this kind of thing, right? In other words, what we're saying, right, is that if you use, right, suppose VT, let's say it's ST minus K plus, okay, as a call option. Or if you prefer, let's look at a forward contract, right? This is forward contract. For me, forward contract is the easiest thing there is in terms of derivative. Then what we assert is that V0, right, the price of the option at time 0, should not be expectation of e to minus RT-ST. Okay. In other words, it should not be expectation in terms of this physical probability, physical model. In other words, right, let's say I should not take expectation of, let's say, oh, sorry, not phi, right, e to minus RT phi ST, because phi is payoff. In other words, it's going to be e to minus RT ST minus K plus in this model, or it's going to be e to minus RT ST minus K in this model. Oh, sorry, in this contract, right? So the question I'm asking, right, is that is E and not E tilde? Where E tilde, right, roughly speaking, we have R here and W tilde here. And here we use E, so the rate of return is mu instead of R. And we claim that if you were to do this accidentally, I hope, right, you don't mean to do it, then it's not correct. But why is it not correct? Or, roughly speaking, right, why do we need the risk neutral framework? And what does it mean? Can anyone tell me? And believe it or not, so this is a question I got on an interview, on a job interview. Why do we use risk neutral framework? And then this comes from a practitioner. They don't want to hear all this, broad motion stuff, right? So why is it that we use risk neutral framework? So why can't you use physical measure to price stuff?
Can I make a guess?
Of course, Cherry.
Okay, I might be wrong, but does it have to be with like deal with like having no arbitrage?
You know what? That was my first try. You know what he was saying? He said there's always arbitrage.
Okay.
Cool as cucumber. No, I think that's right, actually. Okay, now I'm the boss, right? I'm the professor here. I get to say what you say is right. I agree with you actually, but I'll tell you his angle, okay? But you're right. Just maybe not the kind of answer the practitioner wants to hear either. But you're right. But let me press you on this. Okay, what do you mean by that? Why is it that there's no arbitrage here? Clarify, right? Explain.
So I guess the way that like U, D, and R are set up are like in a way that you wouldn't have a significant advantage, like either selling or buying, I guess. Like you couldn't consistently make a profit like using a specific strategy, and like I don't know. I'm not
No,
sure.
it is very good. I think you're really getting the foundation of it, the theoretical foundation of it. But can you bring it home with an example?
Um, I'm just thinking, I think Professor Larson talked about like buying the bank, and then in the case where let's just say the numbers are like equivalent, like if U was the same as R, then you might as well just invest in one. But I can't think of it on the top of my head either.
Okay, so again, right? I think you have the rough idea that I have in mind. Anyone else wants to try? By the way, right, again, this is something that you should be prepared to defend and explain at some point, even at an interview. I really don't mean this as just a theoretical exercise. People may ask this kind of question. Okay. Yeah, I wish I'm Professor Larson. I would ask you this question on the midterm, right, as an oral style. Explain, risk neutral pricing to me and why you care about it. See how you answer it on the exam. Anyway, right, the point is, and I again my style. I like an example that just clarifies everything. Let's look at a forward contract, and of course, right, the question is, what is the price of forward contract at time zero? First of all, does anyone know the answer to this? And second, can anyone tell me how they get that answer?
Wouldn't that be SO minus K?
Roughly, Don, you forgot discounting, right?
Oh, right.
So it's going to be
In
S0
that
minus
case,
K discounting. And again, right, I guess you saw a different kind of discounting in Professor Larson,
right.
how do continuous discounting. Okay, very good. Can you explain to me why that's the formula? And are we using Black-Scholes? Are we using binomial? What are we using?
Hmm.
Why do we get this? Any mod? I mean, are you using some fancy model, fancy thinking here? How do you
I
know
mean,
that?
I'm
Of
just
course,
kind of like based it off on like the first equation, which is like VT equals ST minus K, and then from there, since we already
are you
I'm
saying?
not sure.
I don't think I could hear you. I'm not sure you said something that got cut off.
I'm actually not sure. I'm sorry.
You're not sure. That's fine. No, perfectly fine. Right? Because I like you to think of things like this. The whole point of like trying to understand the framework is to find the easiest piece of information you can. No, it's fine. You should definitely answer. All right. I like you to try to answer. Don't worry about it. Definitely try to answer. What I was trying to say is right that to understand the framework, you should try to question the easiest piece of information possible. And once you understand the logic of it, then maybe you can see, you can extend it to a more complicated piece like this. All right. Do you see, at least you see the implication of, let's accept this. Do you see any implication that is interesting here? Well, there's an interesting implication like this. Suppose K equal to 0. Oh, by the way, right, what is the meaning behind this piece of derivative? What is the action here? What is the description when you buy a forward contract? What does it mean? right? Financially, what does a forward contract imply? And why do people want a forward contract?
If I remember correctly, you invest money until in the initial point.
You say,
At least I think it involves something about reaching an initial point.
so, right, I mean, this,
Contract, yeah.
no, it's fine, but I think you are making this kind of habit or mistake of students who really try to remember and memorize what they learn, right? Rather than just look at what's right in front of your eyes. But that you should try that. I'm just saying that that's very good. Just look at it and see what's telling you. What does the forward contract tells you that it's doing? What it's doing? What is it? What does subtract mean in finance?
We're just taking into the account that we paid K
Yeah,
at the beginning,
you pay K to get.
the final payoff at
Correct.
10. Yeah.
So what the forward contract is doing is very simple. You are locking in a price for the future.
Yeah.
That's all there is. Okay, you're locking in a price because K is constant, right? You see a lot of information goes in here without being explicitly said. ST is random. K is constant. So this piece of action means that you're locking in a constant price for a random future price. And when you think about this, there's a lot of use for this, okay? Because let's say, right, that, I don't know, someone wants, like, let's say Rutgers, right, wants COVID-19. No, Don, please answer, all right? I do not discourage, I encourage answering questions you don't know. I'm not here to pick on you at all. You should answer, all right? I'm just, the more you answer, the more I can explain to you your way of thinking so you can improve. Do not feel sorry about it, and do not, not answer questions, all right? Just answer questions. As long as you try, I will recognize that you're thinking the right way. I'm not saying you're thinking the wrong way, okay? But I'm pointing out that you're making the habit of everyone else. Yeah, do try, okay? Yeah. I mean, do try answering questions. I mean, it makes the class less boring, but also, like, by letting me pick on you, if that's the case, you learn the mistake in your thinking and you can improve. I think that's beneficial, I hope. Anyway, right, going back to the whole point of this, you see that, let's say Rutgers wants to buy a lot of COVID-19 vaccine in September. Okay. Now, you think of it, right, from Rutgers' point of view, right? So COVID-19 vaccine price is this piece right here. From Rutgers' point of view, right, God knows what price there will be in September, right? If there will be, how to say this, like, what they call a wave, right? In September, then you can be sure in September price will go up a lot, right? When you buy in September, because everyone's going back to school, right? Also, from a budget planning point of view, Rutgers does not want to, right, set a contract, wait until September to buy stuff. They want to set the contract now. Yes, but a contract now, but of course, because COVID-19 vaccine is so scarce, you cannot buy it now and store it. And also, it's undesirable for Rutgers to buy it now and store it, right? They want to say, I want to buy it now, but I want you to deliver. I want to get a contract now, but I want you to deliver to me in September, right? When my students come and everything like that. Yes, and I will settle the payment with you in the future. But don't you see that that's exactly right? This kind of very reasonable contract that people would just do every day is a forward contract, right? Set it forward in the future. That's all. But of course, right? Suppose that Rutgers, I don't know, right? If Rutgers doesn't want to sign anything now, right? Don't want to pay anything now, then that's going to be a forward price, right? The futures price, actually, futures forward is similar, right? But if, say, Rutgers want to set a price, right? They want to name, let's say they want to say pay $100 per vaccine, right? So they name their price. Then clearly, right, V0 is what Rutgers has to pay out of pocket right now to secure that contract. Do you see the whole point of what's going on with the forward contract, right? So my point being is that this is a very natural thing that we always do, okay? And I encourage, right? That's why I say at the first day of class that finance thinking, right, math thinking, computer science thinking all go together, right, to make you like a competitive person. If you just stick with the stick with the math, and you don't quite can go back and see the context of the finance, that will make you, you know, like a little bit awkward when you apply the stuff. Anyway, right? So, but I want to explore this from a different angle, right? So let's say k equal to 0. That's kind of extreme, meaning you don't want to pay anything, right, in the future for this piece of product. Then absolutely you have to pay something now, right? And what do you have to pay now? Of course, the formula says that you have to pay S0 now. Yes. Now let's try to see if this makes sense, or this surprise you or not. So what we're saying, right? If VT is equal to ST, then V0 equal to S0. Is it okay? I mean, I guess you see this too much, right? It's like you're getting numb to it. It's so normal, right? There's nothing cool about it, which is fine. But I think sometimes you should try to kind of feel surprised about stuff to appreciate what's going on. Any surprise here about this? Again, right, let me bring it home, because you want to put things in context before you can feel surprised or not. I'm pretty sure everyone heard about GameStop recently, right? You should, at least, even if you don't do finance. If you do finance, you should even hear it more. GameStop, and anyone, you know what's going on with that?
Yeah, I've seen it in the news.
Right. Okay. So GameStop, basically, GameStop being right price of a stock that's pretty cheap, I think $5 or something, right? Became like $300 per share over, I think, a month or something. Yeah, the return at some point is 500%. Okay. So it was so popular, right, that like trading platform, I mean, you know, top trading like Robinhood, right, banned people from buying it. Yes. I mean, this is all fact. You should look it up. I'm sure, I assume that all of you have heard of it already. I'm not saying something shocking to you. But, right, so imagine back in, you know, just 2 weeks ago, GameStop was super hot. You know, and let's say GameStop stock is selling, you know, for, I don't know, let's say at that time it's already hot, $300. And I mean, for those of you who in China, I'm not sure if, you know, you're used to GameStop, but think of like Ant Group, right, from Alibaba, right, from Jack Ma. I mean, I guess it's not very good now, but at some point, right, when they went to IPO, they're super hot, right? And the whole point of super hot stock is that it's hard to get. Yes, people really sell their house to get the stock. But anyway, right, because it's hot doesn't mean it doesn't have a price, right? It has some price. So, and what do you do with this, right? Like, for example, let's say like, you know, because it's so hot, it's not available, right? Someone will say, okay, pay me something now, okay? Pay me something now, meaning V0, and then I will give you this stock, you know, this one share, let's say in a month, right? So meaning, right, you understand this, right? I'm not telling a fancy story or like a crazy to believe story, right? Yeah, there's some really hot stock. You cannot get a hand on it right now, right? Be it GameStop or, you know, Ant Group, whatever. But you need to pay something now, right? For a delivery of that share in a month, you get your hands on it. Okay. So, but suppose it has a quoted price, right? 300. It being so hot, like say GameStop, some you know the broker, your friend, whatever, who happens to have access to it, say, you know what is really hot, right? I know it's selling for 300 now. I want you to pay me, right, something more than that. I want you to pay me 310, you know, for my trouble of securing this option for you. What do you say? Does it make sense? that so basically, right? So sorry, not S0, right? V0. So you will pay more than the current market price to get this stock in the future. Does that make sense? Does this work? Would that be reasonable? You understand the question?
I think that's reasonable because you have to pay. There are buy and ask in the stock market, so maybe sometimes you should pay the ask price.
Yeah, you're right, you're fine, right? That's another aspect of the stock market that we're not we're sweeping under the rug. The bid ask, but bid ask. Let me say, right? Bid ask for me at least, right? Okay, you're getting to the heart of the problem too. So typically speaking, since you bring it up, how large is a bid ask spread? So by the way, right? So Joe will bring up a concept called bid ask, right? Bid price, ask price. You know what this is? I think it's actually useful, right? This is not something theoretical at all. What is bid and ask price?
The bid price is the highest price that the people want to buy a stock, willing to buy a stock, and the ask price is the price that the stockholders willing to sell the stock.
Yeah,
I mean,
correct. So exactly. So suppose you have a product, whatever it is, right? The bid price is the price you can sell. I don't know. It depends on your perspective, but this is the price you can sell the stock to, stock to the bidder, right? Or the underlying, right? The price, right? The ask price is the price you can buy for. Yeah. Let's say the trader, okay? Or the broker. Let me say the broker. Is this okay? I mean, I hope it's clear. So from your point of view, as some poor student who wants to get to the stock market, right? When you look up the quote, they will have a bid price and an ask price. Bid is like, suppose you have the piece of stock right here, a piece of gold, whatever you can sell to them, right? So yeah, think of like you're trying to sell a car, right? Bid price is the price you can sell your car to the dealer. Ask price is the price the dealer asks you, right, for a piece of car, right? The same kind of car. So the natural question is, right, which one is higher? Which one is higher when you see this quote?
ask.
Yeah, this is always less than ask, right? Because they always sell you more than what they buy from you. So the difference between this and this, right? So subtract this is called bid-ask spread. Okay. So I was asking Joe, what is a typical bid-ask spread? How large is it? If you have observed. But by the way, these are experience. There's no round.
I think that depends on the whether the underlying asset is actively traded. I guess if more people is willing to buy the stock, maybe the bid and ask spread is quite small, and
Yep, the bid-ask spread is exactly right. So bid-ask spread is exactly a measure, one simple measure of. So bid-ask spread, right, is one simple measure of something called a measure of liquidity, right? Because you see that basically, actually, I can't do a simple argument in my head right now, but it basically what Joe said, supply and demand, right? Supply and demand from one side can raise the bid price up or down. Same thing for supply demand on this side, right? Can push the ask price up or down. So I mean, you can just tell a story. I haven't really thought of it, so I don't want to say it. But you can see that, right? Basically, these guys will be far apart if there's not much activity going on. But these guys will be right. Not this stock is very hard to find, right? Then this guy will be far apart. That's what your fan was saying. But if there are a lot of these things going around, right? Many people, right? sell it, and many people, you can buy it right away. Then the spread is small, right? So Giovanni was saying that, yes, right here it makes sense, right? It makes sense that you pay more than 300, right, for something, because I guess the whole story I was kind of pretending to tell is that, right, there's no liquidity, right? There's no liquidity in the market, right? So you have to pay something higher to compensate for the fact that that thing cannot be found. Is that okay? So that's perfectly acceptable. Any question? So here's like the point of me telling these stories, right, is to tell you how, right, in the real world or whatever, in some hypothetical situation, it could be real. You know, whatever we say, right, in our fancy model can be violated. So, which is fine, right? But we need to understand why it's violated, under what assumption, or rather, right, we need to know what assumptions makes our model work, right? Otherwise, when we see something like this, we say, no, 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 that's no arbitrage. Then we may look like very inexperienced, right, without knowing what we're talking about. So I agree with Giovanni that, right, that this is acceptable. Of course, right, how much is bigger than 300 is a question, and right, is within this reasonable range that we because we don't have real life information, we don't, you know, we cannot say further. Any question on this? All right, right. And by the way, right, this is why like things like Bloomberg Station and stuff like that, or watching market price is helpful, because these are not something we can just sit here and discuss on papers. Okay, these are things you have to see with your eyes just to have an experience on. Okay. Anyway, so let's now that story is good, but let's now assume perfect liquidity, meaning you can buy and sell at any time. Okay, and that means that, roughly speaking, let's say that, you know, in this class, or in math finance, right, one thing I'm not sure if you ever heard explicitly stated, but it's, roughly speaking, we're kind of assuming that bid-ask spread is equal to 0. All right, now again, right, this is pointing out explicitly where our model is unrealistic in some way, right? Because as Johan or anyone else who has done some trading will tell you, right, bid-ask spread at the smallest, I think, is maybe 1 cent, 2 cents, whatever, right? But it cannot be 0. I don't think I have seen bid-ask spread being 0. But, right, to make our model easy, right, just for pricing, we assume this. So let's go back to the same question, right? Suppose that the current stock price is 300, and you pay money now to have access to a share in 1 month. Then does it make sense for you to pay more than 300 for this kind of product, assuming perfect liquidity?
My take on it is no.
Yeah, Sherry, why not?
I think because I might as well just buy it now.
Exactly, perfect, right? It's as simple as that. Exactly, you might just want to buy it now. Are you crazy? Why would you pay more than that? And that's exactly where the arbitrage comes from, right? The arbitrage exactly comes from the fact that someone makes money off you for paying more than what you should, right? But so you understand, right, that underlying all our pricing model is something little funny like that, right? But we have established that under, right, all these assumptions, if VT equals to ST, then clearly V0 is equal to S0. Exactly like we just said, right? Exactly what Sherry was saying too. Now let's take a look at the other piece of information. If VT is equal to K, right? What is this here? If VT is equal to K, what product are we buying? So this is stock, right? You know, if VT is equal to K, what product are we buying, or we selling, whatever? This is like the bond. This is really like a bond, okay? Because a bond basically at the certain date would give you a fixed face value, right? So this is a bond. Of course, right, you think, well, but the bond is super complicated, right? Why do we treat it so casually? we treat it so casually here because exactly we assume that interest rate is constant and not a function of time, which are both false, right, in the real world, right? And that's why bond price modeling is a big area, right, in math finance, which we'll get to. But you see that, right? That basically this translates to this easily right now because we don't want to get to the bond model aspect, okay? But so these are the two pieces of information. Then the last piece of information is the linearity principle, which I think you have used implicitly in your homework so far. But let's state it, right? Suppose that you have, let's say, product V1 and V2, right? Which has price V10 and V20. Or let's just say they have price V1T and V2T. Let's say you synthesize this, right? Synthesize this and you replicate something. So you have a product V3, but it has an expiration, okay? Which is like, let's say C1, or if you want alpha, right? Alpha share of first product and beta share of second product. Okay, I mean this synthesis goes on, like every time in real world, right? I mean, let's take this S&P 500, right? S&P 500 from some angle, right, is a synthesization of, I don't know, maybe I'm wrong here, but 500 names, right, in the market, right? And of course, there's a weighted somehow, those weighted alpha, beta. What I'm oversimplifying, of course, is that I think the weight changes, or people, adjust the weight, through time. But the point being is, right, there's synthesizing of products going on all the time in the market. But suppose, right, this is so, but from my angle, I'm just saying that I synthesize these two products, right, with alpha weight and beta weight. And the synthesization happens at time big T. In other words, right, at time big T, this third product exactly is equal to this. But what this means though, right, I guess I'm making a big deal out of it. But this means that any time before, their price must follow the same structure. Like this. Is this okay? So I call this the linearity principle, that if at some point, right, the product goes like this, then before they also would follow the same structure. Does it make sense? Why? Because actually it follows from this kind of result right here, right? If you have access to a product in the future, right, assuming perfect liquidity, then the price at time little t must be its current price. If you have some, right, like same thing here, and if you combine them, right, in this same weight in the future, it must be the same weight if you combine them in the current time. Otherwise, I mean, like using the fancy word, arbitrage may happen. In other words, right, if somehow this, just think about it, if this equation does not hold, then if somehow it's a little bit higher or a little bit lower, then you, because of perfect liquidity, right, you can buy exactly this composition somewhere else, and then you can just wait until the end to profit from the difference in the return. Does it make sense? You want more explanation, or I hope this is clear, that this works this way. You use this, right, in pricing the spread, right? Butterfly spread, the condor spread, all those kind of things is exactly this principle that you were using. And I didn't bother explaining more because I think I hope it was obvious. Is it okay? So you see, right, that's exactly the linearity principle that combined to show you that the price of the call option is this. Sorry, the price of the forward contract is this. That's it, right? So you look at the two fundamental, right, pieces of asset. One is stock, and you see how the stock should be priced. right, under perfect liquidity, you see how the bond should be priced, right? And then you combine them using linearity principle. If, of course, the combination is linear, right? Any question? Again, right? I mean, if there's anything that's unclear, please let me know. Some of these I assume that is makes sense, but who knows? My language may be too fancy. Some of you may not catch what I'm trying to say. All right, so now let's go back to the abstract framework, right? That we do from math. Does any of this remind you of any operation that we do, right? Like going from this to this, going from this to this. Does it remind you of any abstract mathematical principle that corresponds with this translation? Anyone? That's fine. So let's recap what you have, right? You're looking for some operation that does what? Basically, right, you see that anything, let's take the stock, right, or any product, right? In terms of pricing, what you're saying is somehow, right, let's say the whole point is you want to translate, right? Do you recognize that mathematically you try to translate the action from time big T to time small t of price? That's all you do, right? That's exactly what pricing does. You translate something from the future to the present being little t. That's what you do. Okay. From our financial principle, right? Please notice, the point I want to make is all the things I'm talking so far are pure finance, no math in there, right? These are something that someone who has seen how the stock market works or the finance market works under perfect liquidity should say the same thing as we do, okay? But now, right, the math comes in to capture this in an abstract formulation. How? Well, so first we recognize that all we do is translate something from time big T to time small t. Now, from the finance angle, doing that, first of all, take some kind of discount, right? Where here is the discount from time big T to time small t. Yes, it's a discount. And then, of course, you see, but by whatever we're saying so far, the discount should happen like this. Yes. Second, right, it should translate a constant to a constant. So the difference, right? This is random, right? VT is a random process. But if it's constant, then like this. And finally, it follows linearity principle, right? If you discount, then you got am I right? I'm just recapturing the finance in terms of what the translation does.
Expectation.
It's exactly expectation. It's exactly conditional expectation. Do you see? Expectation translate constant to constant. Expectation preserves linearity. Finally, right, this is not just expectation. This is the martingale structure. Isn't it? So that's why, right, we come and search for some kind of expectation such that the discounted stock price is a martingale. And because if we price things like this, then we preserve the martingale structure. In other words, the discounted this is also a martingale. Am I okay? Am I clear or not so clear? So you see that the math, right, maps exactly, right, what you expect in the finance into an action call conditional expectation with the martingale structure. The martingale structure, you see, is already there when Sherry was saying that she will not buy anything different from S0. That she already implies that she is looking at the martingale without, of course, recognizing that's what she's talking about. Any question? Okay. So this is why, right? So, okay, but once you establish this, then you revisit the model you have. In other words, let's say now you revisit the model, right? This model. I mean, like, okay, we call it physical. Why? Because it's something that we believe that the stock really moves like that, right? You observe the stock in the history, you see that its return rate is really mu. I mean, that's why you call it physical, nothing more. And then you say, you go ahead and check, right? Is the martingale structure get preserved, right, under this model? And I hope, right, that you see we have done enough calculation, right, that you see that this is not true if the rate of return is mu. So yes, right, you can tell the story from, you know, what Sherry was saying before. I think that's what Professor Larson does, right? I mean, you can reconstruct the portfolio and show that you really make an arbitrage, which is perfectly valid. And I would be able to do that too, right? But I would like to bring home even an easier story, right? Maybe less rigorous, but I would say more intuitive, that just observe, for me, right, is modeling, right? Just observe what's going on in the pricing action in real life. The method we do is supposed to capture, right, this action. If it doesn't, then we cannot call what we do modeling, right? So there, right? I hope that, right, by seeing, right, that the physical model does not capture the what we expect from the pricing, right, that we would see in real life, we see that maybe something like this, but not this model, right? So therefore, you say, I I I really want somehow this to happen. And the transition from here to here, right, is the so-called risk neutral change of measure, which we'll discuss next. But right, unless you're convinced that this is absolutely necessary or is absolutely corresponding to reality, right, you may not appreciate, right, all the math, all the work we come in to establish that this is possible. Okay, so I spent all this time to tell you that it makes sense financially, right? Our work here is to supply the mathematical foundation to explain, to model what happens, what's happening. Any question? Is this okay? Makes sense? Too easy? Too trivial? I mean, if it's too trivial, let me know, right? I don't want to bore you. If this is something that you have seen before, everything like that, let me know. How are we doing here? Fan, this is all stuff for you. This is too simple, too elementary.
Kind of.
Okay, to kind of. So you want to see more hard stuff. All right, all right. Okay. Is that the case? Is it understandable so far? All right. Okay. So I mean, let me know as a class, right? I mean, because I think some of these things may be obvious to someone, maybe not so obvious to others, right? And I like I said, the point of view I want to bring in is why you need the math. All right. I trust that you can work on the math yourself, but if you don't see why you need the math, maybe, right, you just don't see the connection at all. So if I'm wasting your time explaining this connection, let me know, okay? We can do more math. But if you need this connection, then also let me know, because yes, right, this is what I'm willing to spend time on, okay? All right, so what do I want to go do next? All right, yeah, so the next thing I want to say is this, that, so this is the story I'm telling you so far, but in an interview, right, you go back to what I was talking about from the interview point of view, you're not gonna tell the interviewer all this kind of fancy stuff that I was talking about, right? I think this is a good angle to explain risk neutral pricing, but from some other angle, right? This is not you're supposed to give like one line answer or something like that. Okay, so let me tell you another angle to risk neutral pricing. Okay, so that angle has to do with the word risk, right? What does risk mean? What do you think risk means in finance? What does risk mean? So risk for finance always means something uncertainty in the future. Okay. So the fact that you get something, you get a random payment like this means that you're exposed to the risk in the future. So the fact that you're exposed to a random payment in the future means that the option holder, is exposed to a risk. Okay. Yeah, and by the way, right, the uncertainty can be positive or negative. That's the fun thing. Meaning, in other words, even if you're guaranteed somehow to get positive payment, think about it, call option, right? Call option guarantees positive payment, right? There's no way you will pay money on a call option, yes? But still, people talk about the risk of a call option, yes? So when you buy a call option, you can talk to anyone, right? You buy any derivative. I don't recall any derivative on top of my head unless it's short. But if you buy it, right, then you're in for some positive payment, right, not negative payment. But still, right, the consensus is you are exposed to risk. Okay, so basically any random payment in the future, that's risk. So how do you price a random payment? And that actually is another angle that actually I believe that this gentleman who was interviewing me was kind of looking at. All right. And by the way, it really is the angle that some people, practitioners, take out there. All right. Our point of view is more of an arbitrage point of view. That's the classical traditional school of thought. But the pricing the random payment is another way they look at it. Let me tell you, right, an example. It really gets motivated by gambling. Okay, by gambling. So for example, suppose that, let's say you flip a coin, okay? Let's say head, and let's say it's fair, okay? Let's say head, you get $10. Tail, you pay me $5. What's the price you pay for this game? What's the price you're gonna pay for this game? Let's say it's fair. So one half, one half. What price you will pay me for this game?
2.5.
Yeah, 2.5. And your justification is?
We can do a expectation.
Yeah, okay. Does everyone else agree that this is the price? So let me ask, right? Why? Why is it the price? Because of expectation. So you notice that if you answer this kind is like that, then you are not really answering the question because you're using the answer, right? You're using the answer to answer the, you suppose the answer, right? Because why do you price by expectation? Because expectation. What does it even mean? Okay. Let me demonstrate to you, right, that this concept is a little bit iffy. Suppose that you flip a coin. Okay, same question. But let's change the head and tail probability like this. Let's say it has 0.01 chance of head and 0.99 chance of tail. All right. And let's just, let me make it easy, right? Let's say 100 and minus 100, like this. Okay, head you get 100, tail you pay 100, right? Wait, is this okay? No, let me just make it even better, right? Because I think it's this, then let's say head you get 10,000, right? Is it okay? I think that will make the math correct. Yeah, so what's the price for this game? The price for this game is $1, right? Am I right? If you go with expectation. Am I correct? So let me ask you, right? Cherry, right? Let's say we play this game. Me and you, right? Real money, right? So we flip something that has 1% chance of coming up, 99% chance of not happening. If it comes up, I give you $10,000. If it doesn't, I'll just ask you to pay me $100 for my trouble. You want to play? We can play right now.
No.
I'm serious. We can play right now. Just don't tell my boss that I'm, gambling with students. But will you?
No, I don't want to play.
Really? But you just tell me the. Oh, by the way, right? You have to pay me $1 too, right, for my trouble, right? But I'll be generous. I offer it to you for free. Right? I'm very generous. Right? You're supposed to pay me $1. No, just play it. You want to play?
No, it's too expensive.
Too expensive. Oh my gosh. It's supposed to be, am I wrong? The math says it's $1, right? I'm giving you an arbitrage, isn't it?
Oh, wait, you're saying that I pay $1 to play the game.
No. Isn't that $1? Does the price means that, no?
Then what is this tails or
Oh, sorry, tail, right? Tail.
yeah, what is this tails minus 100? Like,
yeah, but what do we mean by price?
to play one round?
Yeah. So
But then I'll just lose the $100.
isn't that the point, right?
Yeah.
Think about it a little bit. So what do you mean by price when you so happy to give me 2.5? Don, will you play this game with me? Again, I'll offer you, free money. I mean, you don't have to pay the entry
I don't think I would, of like the expectation of how much I could earn from just playing this game.
So do you see that there's anyone else wants to play this game with me? So I hope, right, that you see the point, right, is right, that I just demonstrate to you that this is a random payment right here. This is a random payment, okay? And immediately your risk attitude comes into play. When it's one half, maybe you don't feel anything too painful about a 2.5. But when somehow the risk or whatever, the odds is skewed, suddenly, you start to become risk averse. Meaning exactly like Sherry said, it's too expensive, right? You feel like, right, even if you don't pay anything, that's still too expensive to play the game, right? Sorry, Sherry, right? Sherry said use the right word. In other words, expectation doesn't have to be or should not even be, right, the way to price something, okay? You know why you always get the routine answer, the expectation is the price to pay again, to play the game? Because of the assumption that you will play this game a million times, or at least 1,000 times, okay? When you answer with expectation, there's always that kind of, assumption that if you play this game 1,000 times, you think about it, right? Then one of those times, or I guess 10 of those times, you will win 10,000 on average. And of course, a lot of times you will lose, but you only need one big win, right, to compensate for all your losses. Does that make sense? So in other words, if you have the time and the money to play this game many, many times, then this price actually will make sense. But of course, right, in real life, we only do it once. Or with option pricing, you only do it once. So the pricing, right, by expectation for a game that you play once does not make sense to use expectation per se. In other words, pricing by expectation is not automatic. Is that okay? So let me just, it's not the topic of this class, so let me just make it real quick. Basically, the point is this. Suppose you have a random variable x, okay? Random payment x. What is the price for x? All right. In other words, right, like this, right? The random payment is 10 and minus 5, or 10,000 and minus 100, right, with this kind of probability. How much, right? Price means a constant, right? So basically, you see you're trading a constant for a random variable. You're trading a constant for a random variable. You're exchanging it. There's no rhyme or reason to do this, right? I mean, there's no rule in the universe that would establish this. What we did before was establishing a martingale rule to do so, based on trading, based on replication. Here, right, there's no rule for it because there's no replication. But there's still this idea of the risk attitude. So the answer actually depends on the risk attitude. Meaning depends on your risk attitude. Okay? If you suppose that the price that you want to pay is equal to expectation of x, then you are being risk neutral. If you think that the price is bigger than expectation of x, right? Meaning that the let me see, then you should be risk averse. And if you think the price is less than this, then you should be risk seeking. I'm wondering if I'm saying in the wrong direction. Maybe I'm wrong. So here, price in the sense of you have to pay for x, then I think it's the other way. Okay. Exactly like Don said, right? Or sorry, Sherry, right? That remember I said, right? Even if I offer you to play this game for free, you do not want it, right? So in other words, for you it's less than expectation, but much less, right? Much less than one should go into a negative, meaning I have to pay you to play this game, right? But someone else you may imagine, right? Someone else who would love to have a chance to win $10,000, right? They would say, yeah, I pay you even $2 to play it. Does that make sense? So you see that. So basically, risk neutral is saying that, okay, I don't have information, so I just use expectation as the price. So basically, the risk neutral person does not have any preference over a constant payment or a random payment. The risk averse person, I guess, should prefer the constant payment over the random payment. The risk seeking person prefers the random payment over the constant payment. Okay. Now I'll say one last thing, and this is it. I'll move on. But what some theory, okay, some theory of pricing does this. Price it by saying that you do expectation of a function of x. This is not the option function, but phi is called the utility function. Okay, phi is a utility function. So it's a very fictitious object. Okay, but basically suppose that I have a way to capture how Sherry feels about the random payment. In other words, phi is some kind of, I don't know, I forgot, it's concave or convex function. Basically, it says that, you know, depending on the range of the payment, you see. Notice that when it's in the middle range, then I guess, you know, maybe, you know, everyone's neutral about it. But when it gets to like the skew region, then people start to price it differently. So this is supposed to capture that risk preference. Okay, phi captures the risk preference. And to make the long story short, that's exactly what that gentleman who interviewed me, right, was telling me the answer he was expecting. This was with Moody and Poor, Moody, right, Moody rating. They do, you know, credit rating. So I don't know, maybe they care about this kind of stuff. That he was saying, right, that the reason why we do risk neutral pricing is because we do not want to model the risk preference of the clients. That's what he said. So basically, you assume that the clients are risk neutral. To him, it's an assumption. If you know the client, right? If you know the client, you know their risk preference, then you can price it more precisely, right? You think about it. Suppose that you offer this game, right, to someone, and you know this person is risk seeking, then you can tune your price up, right? Why would you offer him at the expectation? You can charge him more because he's willing to pay more. But if you the same object, but to someone who's risk averse, then clearly you cannot sell to that person at the expectation. You should dial it back. But you know, in the vast world of customers, you don't have much information. You use expectation. All right, but I'm telling this story so that you can see there's a different point of view, right, to risk neutral pricing. The message I want to make is that in some circle of the practitioner, saying risk neutral means that you assert that the price is equal to expectation. That's all. But of course, right, for us, it's not enough because what kind of measure are you using? Are you using risk neutral probability accounting? But all right, so, but this is a real, okay, this is a real angle people use to approach pricing stuff. So I want to bring it up so you're aware of it. Okay. So all in all, right, it all circles back to the idea that we want to price by expectation, okay? And we want to make sure that under our pricing, the stock price has a martingale structure. And that's why we use risk neutral framework. Any question? All right, so maybe enough about the finance, all right, or this all kind of modeling. Now let's get back to the math. So now the math would ask us how to do the change of measures, okay, in Black-Scholes model. The math would ask us how to do this rigorously. All right. So what's going on? So what happens is we have this model, physical model. And we have the suggested, right, risk neutral model. So immediately you have questions. How are W and W tilde T related? Okay. And let me say this, right? This is the under P, under some physical probability. And this is under P tilde, under some other probability, okay? A different angle. And then how are P and P tilde related? Okay. So what do we know? We know that WT is a Brownian motion under P. W tilde is a Brownian motion under P tilde, right? So first, let's address this question. How are WT and W tilde related? Are they the same? Are they the same object? How are they related?
I might be wrong, but I'm just guessing that they're both based off that normal distribution, so they should be the same.
Good question, good answer, but that's exactly the mistake, right? And then I know people usually think about this a lot. I make this mistake a lot too. What you're thinking, Sherry, is that they are the same in distribution.
Yeah.
Okay. So in other words, what we're saying is distribution-wise, they're the same, which is you're right, because they're both prime motion, right? But actually, just to kind of give you a clue, right? Suppose you have two dice, right? First die, second die. When you roll them, do they have the same numbers?
Oh, not necessarily.
Correct, right? If you have two dice, of course they're the same in distribution. In other words, right? Abstractly, you think they should give you the same chance of getting different numbers. But the fact that they're not the same is because they're different dice. But another, right, because you roll them, you don't get the same numbers, right? So same thing here, right? They are not the same object. And this is, you know, like people tend to think like this. The reason is, right, you just transition, which is fine. Like I have no problem with this. I will do this also, right, later on. But the movement, right, from this to this, it requires some careful analysis. And it's really a physical relation, all right? It's really a physical relation now. Basically, you start from the physical model. Now you want R here, right? But of course, this is this, by the way, this is a stock price return, right? You cannot change the return. The return is a number, right? You think of it like this. Return is a number. WT is a number, right? DWT is a number. Like you think of it like you generate this in a program, right? You already have a rounding motion path. You already have a stock path, right? These things are fixed. So if they're related like this, if you insert the R in, you cannot keep the WT, right? How does it change? If you insert the R in, you can see that, right? You must recompensate the mu, and you need to subtract the R. Is it okay? So I subtract the R. Of course, I divide by sigma to get it back. And then I reintroduce the mu back. Okay. So comparing the model, right? Comparing the model, you see that this is exactly W tilde. Okay. So in other words, W tilde is W. This is in terms of the differential model. And you see again, right, why immediately Ito's formulation is relevant. Because, right, you say W tilde is dWt plus something dt. That's Ito process, right? You see how Ito process immediately comes back. Is this okay? Or if you want, you can integrate both sides, right? If you integrate both sides, because W tilde 0 is 0 and W0 is 0, then you just integrate this. But of course, this is a constant, so it becomes is that okay? So that's the relation between W tilde and W. Now, this quantity, right, the mu minus R over sigma, is a very special quantity, and it has a name in finance. Does anyone know what name it is?
Sharp ratio.
Yes, it's a Sharp ratio, and it's supposed to tell you what? Why is it important? What does it capture?
I think it captures the returns of the strategy.
Not precise, right? Because returns have many things. Returns can be just mu, no? So when you say it captures return, you're not being precise. Because like I said, like, you know, like mu is a return. Why mu minus R over sigma is a return? Anyone else? So return is close, right? But this is called the risk-adjusted return. Or if you really want risk-adjusted, I think it's called excess return. Okay. Why? First of all, right? Again, it's just finance. Suppose, right, you think about it. Suppose R equals to 0.02. If a company has returned 0.01, is this even a good company? Or is it even a real company? Should not be, right? Because if the risk-free rate is 2%, why would you invest in a stock that has average return of 1%? Okay, but I'm giving you a silly question like this, silly thing like this to show, right, that it's not really this number you care about. You care about this number relative. Yeah, right, sure. But you care about this number, right? The return. You don't care about the return of a company in a vacuum. You care about the return of company relative to a risk-free rate. Okay, and it has a real meaning, right? Risk-free rate is really low right now, so no one bothers. But suppose, I don't know, I'm not sure if inflation or something, right? In inflation environment, inflation high environment, let's say, I don't know, you have 7% interest rate. I mean, it's not impossible, right? Then again, right, a 5% return is usually good, right? In the normal market. Is a 5% return acceptable here? Absolutely not, right? Again, for same reason, and even for that matter, even like a 0.09 return may not be that good, because a 0.09 return, you see, a 0.09 returns here is the same as a 0.04 returns here in terms of excess returns, right? I think, I hope that's the term, I forgot already, but it's basically return above and beyond risk-free, right? I think it's called excess return, right? You see, right? So you care about the return relative to interest rate. That's the first concept. But that's not the end of the story, right? Because suppose that you have these two companies. Suppose the first one has volatility at 10%. The second one has volatility at 50%. Which one would you prefer? Right, I guess forget the interest rate. Let's just keep them in the same interest rate environment. I hope, right, everyone would prefer the first one. Yes, right, it's less risky. So you see, that's why you want to penalize or, scale back by the risk or by the standard deviation, right? This should also remind you of some kind of Z transformation too, right? But anyway, so Don, right, actually you should work backward, right? It's not because we want a higher Sharpe ratio, so we want this. The Sharpe ratio is constructed, right, to capture exactly these pieces, how they fit together, right? We want high excess return and low volatility, I guess, right? So the Sharpe ratio is constructed exactly, right, to capture this information, right? But yeah, I mean, thinking forward is fine, but I feel, right, it's sort of like reinventing the wheel, right? I mean, not that there's a magical object here like this that has some higher purpose, right? We construct this, or we name this object because it has this kind of thing, right? So the highlight term, right, is risk adjusted, right? Risk adjusted means this sigma right here. Sigma is a risk. Excess return for the par, okay? But you see that to say that I mean, I don't know, to show that the whole transition to risk model, right, to risk neutral makes a lot of financial sense as well, is you see that, right, transitioning from physical model to risk neutral model is in a way taking the Sharpe ratio away. Taking the Sharpe ratio away, right? You see that generally speaking, the Brownian motion, right, has this is the earning of the company, isn't it? And this tend to be positive, right? This is a slope, the slope of the risk adjusted return. By calling this whole thing dw tilde t, you see that you say that you do not care, right? It might as well be zero, right? That basically you neutralize out the whole Sharpe ratio. You do not look at the Sharpe ratio of a company when you transition to the risk neutral framework. Any question here? Okay. So that's how are W and W tilde related. Okay. Now, the more important question, or the harder question, is how are P and P tilde related? Like this, all right. Basically, just because you change, right, you change WT, right, and then you have W tilde T to be, let's say, right, mu minus R over sigma times T plus WT, right, like this. So let me ask you this, right? Let me ask you a very simple question, right? WT is a Brownian motion, right? It's a P Brownian motion, let's say. It's a Brownian motion in a physical measure. Is W tilde a p-Brown motion? Is W tilde a p-Brown motion? Yes or no? No, perhaps, right? Why yes? Why no? Why perhaps? I mean, okay. I say no, perhaps already. So I guess perhaps means yes, right? Yeah.
My guess is that since like had WT includes WT, which is related to P, then that would mean had WT would also be related to P in a way.
Yeah, okay. Related to P is a different question than saying is a Brown motion, Don, right? When we say something is Brown motion, we have very strict, right, concept of what it is. That's what math is about, right? We say something is something, we really mean it. So for example, what kind of properties come in for Brown motion? It must have mean zero, right? Variance something something, right?
Mhm.
Brown motion is supposed to be centered around zero, right? It should not contribute to any noise. What is expectation of W tilde T? Well, because WT is a Brown motion, right? So expectation of WT is zero. So the expectation here should be this, right? And if we assume that mu is bigger than R, as the case that should be, otherwise that company should not be even existent, then this is not zero, right? Or in fact positive. Is that okay? So the fact that it's something like this means that it cannot be a p-Brown motion. Is that okay? Maybe it's hard to see, right? Because also, right, just think of it from the point of view of noise modeling, right? I mean, I'm not sure how many classes you've taken that has some noise component to it, like regression, right? If you run regression and you have the noise left, you usually want to have the noise to have level 0, right? Besides artifact, right? If the noise has a mean that's changing, there's some signal in it, right? That's not pure noise, right? Pure noise should have nothing left to be modeled, right? So the point being is W tilde is not a p-Brown motion, okay? And that's why there is a change of measure, okay? There is a change of measure from P and P tilde. A change of measure from P to P tilde is necessary, right, to view W tilde as a Brown motion under P tilde. All right. So that's the whole that's the method we will be discussing for a while now. How does this change of measure happen? Okay. And like I said, right, we're gonna go into a very, heavy duty mathematical stuff. So I want to make sure that you understand why we want to do this before we do the math. Otherwise, you super get tuned out from the fact that we're just discussing some dry math. But this math is necessary so we can support the framework that says we want to do a risk neutral pricing. Okay, we want to do a risk neutral pricing. So how to define a change of measure. So here I really have to quote Professor Larson, all right, that I hope he does a good job teaching you all these concepts. But first of all, you should know something like this is a sigma algebra. I don't bring this up too often in this class, all right? And I would not really harp on what sigma algebra really does, but you should have a rough idea what sigma algebra is, I hope, right? Second, you should know that if S is less than T, the sigma algebra at S is no more than the sigma algebra at ft. Yes. So this, right, represents information flow, right? This is supposed to model information flow. So there is the biggest sigma algebra is ft, right? The biggest sigma algebra is ft for t less than or equal to t, because from our pricing point of view, right, our horizon stops at big T. So the biggest information we have is on big T, right? So sigma algebra is where you need to define your probability, right? Your probability makes sense on the sigma algebra. So that's like the domain of the probability, if you will, right? So if you define the probability on this, then you automatically defines the probability on all the smaller sigma algebra. Is that clear? So it explains, right, the following thing. Suppose I have an x, okay, a random variable in the biggest sigma algebra. Let some random variable z, okay, be a positive random variable whose expectation is equal to 1. If I have such a random variable, then I can define a new probability on this sigma algebra generated by z, okay, as followed. The expectation of this random variable x under the new probability, okay, and let me call this new probability p tilde, okay, and let's say p is the old one, okay, p is the old probability measure. Then e tilde x is defined as expectation of z of t times x. Like that. Then I claim this defines a consistent new probability p tilde. Okay, so first of all, is this old stuff or new stuff? Have you seen this before in Professor Lawson's class? So I can go fast. Okay, you have seen it. All right, very good. So you understand what's going on here, everything. I don't need to repeat more details on what's going on behind the scene. All right, I trust that you are great students. Oh, you know what, Cherry? Expectation of Z. I don't know why my pen, I guess, yeah, Z. So Z here is a change of measure kernel. Okay, so let me give you an example right away. The example that we will be using is something like this. ZT is e to the minus 1/2 theta square times t minus theta times WT. Okay. Let's check that ZT has all the property. For example, is ZT non-negative or is ZT positive? Actually, I think here you just need non-negative, really. You don't need positive, but is ZT positive here?
Yes.
Yes, right, because it's expectation. Oh, sorry, it's exponential, right? And expectation of ZT, I hope, right, from working with the Brownian motion, you understand that this part here will have this expectation. So therefore, expectation of ZT is exactly 1. Okay. Now let's demonstrate to you, right, what's happening. For example, what is expectation of WT under the old measure? It should be 0, right? Do you think expectation of WT under the new measure is 0? Yes or no? Well, let's see, right? What is this by definition? To find the, expectation of any random variable, under a new measure, you just write back in the old way, multiply with the kernel. Okay. And basically, right, whatever question you want to ask about here, you can just ask on this with the kernel. So I asked if this is 0 here, that means is it 0 here? Right? Do you think it's 0 here? Why yes, Don?
Because the expectation involves like the exponential multiplied by WT, and since we already know that the expectation for WT is 0, then by multiplying that with the exponential, it'll just end up being 0 as well.
Very good, except you make a fatal error.
No.
Because when you factor out the exponential, what are you assuming? You're assuming the exponential is constant, isn't it? But is the exponential constant? It has WT, right? You can't factor the whole exponential. Yeah. So in fact, right, it boils down to there is something you can factor, right? This part right here, which is constant. So yes, you're partially right, but you missed, right, this WT. So this WT right here cannot be factored out. So roughly speaking, right, if you are considering whether it's 0 or not, you are looking at this. Okay. Now, is this 0? Because why do you think it's not 0? Well, let me give you a hint, right? It basically, and you should recognize this mathematically. This is roughly the correlation between or covariance between these two guys, right? When you see expectation of product, you can think covariance, especially right when one of them has expectation 0. So this exactly is the covariance of these two random variables. Now, do you think these two guys are uncorrelated? Should not, right? Because they are, they're the same Brownian motion. Now, there is a small chance they're uncorrelated, okay? There's a small chance. It's just somehow the distribution works in a weird way like that, but I do not think so, right? I do not think so. I think this is not 0, okay? So I'll leave it for you to check. But yeah, right? So the point being is, right, it's really a change of behavior. In other words, right, you have a Brownian motion that has expectation 0 under the old probability. The Brownian motion does not have expectation 0 under the new probability. Okay. I mean, so in that sense, you shouldn't call this a Brownian motion anymore, right? So now when you say Brownian motion, you should qualify under what distribution, okay? Is it under the physical probability or under the risk neutral, right? Clearly under the new one, sorry, right? We didn't say risk neutral. Under the new one, right? It clearly is not 0 if this calculation works out. So it cannot be. Okay. All right. So what does it have to do with anything that we are discussing so far? What we're discussing so far is how to go from P to P tilde, okay? So that this guy right here is a P tilde Brownian motion. That's what we're discussing, okay? So our question, how to go from P to P tilde so that W tilde, which is mu minus R, and by the way, right, okay, let me just leave it like that, like this for now, over sigma T plus WT is a P tilde Brownian motion. And so the answer is, well, okay, not the answer, but so from what we've been talking about so far, this is equivalent to asking, okay, what change of measure kernel we use. Okay, because if you, right, you see the whole change of measure is established like this. If I tell you what I use, then you will know, right, how to go from P to P tilde. Is that okay? And so without any suspense, right, let me give you something, the main result. So the main math result, okay, is called the Gasanov theorem. It says that let, right, ZT be e to a minus exactly what I just wrote above, 1/2 theta squared times t plus theta WT, sorry, minus. Okay. And do the change of measure kernel, right, like we use, right? So define expectation tilde of x, right, is equal to expectation of x times ZT. This is for x in the big filtration. Then, right, W tilde t, which is WT plus theta t, is a P tilde Brownian motion. All right. So that's Gasanov. That's Gasanov. Now, all right. So first of all, what the heck is it saying? And second, how is it related to what we're asking? It basically, Gasanov theorem in our context tells us how to change the drift of the Brownian motion, right? The dt term is referred to as the drift term, okay? The dt term is referred to as a drift term. The dwt term is referred to as the volatility term, right? I guess, I'm not sure, is it a volatility term? Yeah, but this is a drift term, okay? So the Gasanov theorem says that to add a drift, right, of theta times t into, right, into the Brownian motion, the old Brownian motion, and call it to have it to be a Brownian motion under the new probability. This is exactly the change of measure, the change of kernel, right? The change of measure kernel you use, where this theta is exactly the same theta. All right. So you see, right? Then you only have to apply it to our current question, where theta then is this guy right here. This is theta. Okay. Theta is mu minus R over sigma, right? So in our risk neutral framework, we apply Gasanov theorem with theta equals to mu minus r over sigma. Any question?
Does this have any like relation to the format of the exponential term that we use in Black-Scholes?
A lot.
It
A lot.
looks very similar to that.
Yes. Yes, very good question. Exactly, we'll get to that, Cherry. That's exactly the next question. Because actually, maybe my first question is, do you see anything mysterious about Gasanov's theorem? Right? In other words, suppose you want to understand what Gasanov's theorem is about, what's your first question? Your question is also relevant, or right there, right, Sherry, but it's not quite precise, right? What is the precise question you want to ask if you want to understand Gasanov's theorem?
Well, at first I wanted to ask what theta was, but then you explained that it was the Sharp ratio.
But that is applying Gasanov to our context, right? Now we're focusing. So you understand Gasanov is a generic theorem where it allows you to do any theta, right? So here, this is applying it to our context. But to understand Gasanov, meaning we just want to focus on this abstract context and understand how or why it works, then what kind of question do we want to ask? That's my question for you, if that makes sense.
I'm guessing again, but what, like, under what situations can we apply this theorem? For what?
Not really, because I mean, I guess it tells you that you can apply it for Brownian motion chain of drift, right?
Oh, okay. Then I'm not sure.
I guess the question I'm not sure is only obvious to me or not, but what does it mean to be a p tilde Brownian motion? Or for that matter, what does it mean to be a p Brownian motion? Right? Because when you say, okay, you do this and it's a p tilde Brownian motion, how do I trust you? How do I know you're right? Yes, because I mean, I guess maybe this is not something you pay attention to, but why? How? How is, because right, as I was demonstrating to Dawn, that right, if you have a expectation that's non-zero, you cannot claim that you're a Brownian motion, right? So obviously, right, among many things else, the expectation, right, under tilde of W tilde must be 0, right? But that's not enough, right? That's not enough. I mean, to establish that something is a Brownian motion, you have a lot of things to establish. Okay. So my point being is this, that to establish something is a Brownian motion, you can go back to definition, saying that it starts at 0, it has a normal distribution, that kind of thing. Okay, it has a normal distribution, that kind of thing. But establishing, right, W tilde has a normal 0t distribution under P tilde is not pleasant. Okay, so for example, let's say to establish that W tilde has a normal distribution under P tilde, then you need to establish something like this. Let me do less than, right? Okay. So you understand, right? This is the density of a normal with mean 0 and variance t, which is what exactly W tilde is supposed to have. So to establish, right, that it has a normal distribution, then you need to establish something like this. Under P tilde, Do you have any clue on how to do that with this change of measure kernel?
Wait, sorry, I'm confused because I'm looking at the definitions of the Brownian motion and I don't see like probabilities mentioned, but you're saying that they're like implicitly mentioned in the integral.
Okay. Now, if you don't mind, can you tell me what the definition is of a Brownian motion?
Well, we have the fact that like W0, 0, we have zero increment and then independent increment.
Sorry. So independent increment, fine. What's the second one?
It's I don't know. It's the WT minus WS. Takes on the distribution of like normal with variance T minus S. Yeah.
Yeah. Very good. So first of all, if I apply this with S equal to 0, how does the statement read?
Mean zero variance T.
What has mean 0 and variance T?
The normal distribution.
Yeah, but what has normal distribution?
Oh, the Brownian motion.
Not just, so WT, right?
Yeah.
I guess I'm just pressing that point, but WT has normal 0T, right?
Yeah.
Okay. But if WT has normal 0T, what are you saying? What do you really mean by that?
Oh, so the probability we're calculating with the CDF and everything.
I mean, right? I mean, that's
Okay.
really it. I mean, like, if you really need to do it, right? I mean, suppose someone asks, okay, you say something is abnormal. Convince me, right? Exactly like your homework, actually, homework 3 of this week, right? I asked you to convince me that some kind of integral is a normal. What do? Well, I hope that you graph some histogram, but you recognize that by graphing the histogram, you're mimicking the density, right?
Yeah,
So this is exactly just writing that fact down, right? Of this, right?
Okay.
Or if you want, right, you can just copy this down too. But you see, the reason why I write as a probability, I have a reason, okay? Yes, what you say is right too, Cherry. Yes. But the reason why I write it down as a probability is because, right, the connection between W and W tilde is by the change of measure kernel. Is not through some writing down something like this. So writing a probability has some help, has some hope. But writing something like this down, I feel like, right, just doesn't have any connection with change of measure. You understand what I'm trying to say?
Yeah, I understand. Thank you.
No, it's fine, right? Yeah, do definitely ask question. And it's really a hard math result. It's not an easy math result. Okay, so that's why I want to spend the time explaining the whole context, right? Because, for example, how would you convert this to a probability involving WT? Right? I guess I did not mention this because you say you have seen this, right, under Professor Larson's teaching. So yeah, right. Tell me, it's a change of measure, meaning I should be able to change probability back and forth, right? So how do I compute this probability? If you claim that you have learned it from Professor Larson, tell me how. How do I compute this probability? Again, right? Don't feel ashamed if you cannot do it, because that's fine. I understand. You know, sometimes you just forget stuff or you don't quite understand stuff deeply. That's the point here, right? I can re-explain everything to you. But if you do, then I don't need to mention this very much. Can anyone tell me how to go from here to here under the change of measure definition kernel that I use? So it is clear, right, that expectation of, let's say, oh, by the way, right, so it's not quite clear yet because I use little t here, all right? I use little t here. There's some subtlety here. This is big T, okay? This is big T. And this is little t. So there's some subtlety here. But let's just stick with big T for now. Let's say I want this, okay? Let's forget the little t for now. If expectation, right? If I want to compute expectation, then we establish, right? It's going to be just this. So for that matter, right? Something like this, I hope is clear, is this, right? What I'm interested in okay, fine, they're all expectation, but I want probability. You know why? Because exactly what I've just been discussing with Sherry, that I want to see if it's normal, right? Can you tell me how to write this down? Well, so first of all, do you know? Yeah, Jofan, you want to say something?
Should we write a indicator function?
Absolutely, that is exactly the point. Probability is also an expectation. And that's why when we say certain thing, we do not need to state probability statement, because we understand that the reader can just convert it to an indicator statement. Okay? Is this okay? Because Johan said it, I hope you have seen it in Professor Larsen's class. He was trained under me too, so I don't know if he got from me, from Professor Larsen. So if you don't understand what is this, let me know. You understand indicator function, right? You do, you don't? So indicator function of a set, right, of a random event is going to be 1 if E happens, and 0 if E does not happen. Right? So when you take expectation, so sorry, right, maybe I should not use E because E here kind of confused with expectation. So let me say event A, okay? So expectation of indicator function of A actually is just probability of A happening. All right, because you integrate over 1, so you're adding nothing but just the probability. So that's exactly it. You just convert it to an expectation, then you can just convert it back to, oh, I apologize, right? Here I should keep W tilde, okay? Because I should convert it back to this, but I should keep the W tilde, all right? It's not W. So in other words, if I want to do one more step to convert it to W, I will convert it back to WT plus theta times T. Is it okay? It's crucial. It's crucial, all right? It's a mistake that I think you guys can also make. That basically, right, converting E tilde to E means multiplying with a ZT. Converting W tilde to W means adding theta T, because that's the hypothesis. Okay, so those are 2 different steps, right? Don't confuse them. So when I go from E tilde to E, somehow I drop the tilde here, and that's a mistake. So same thing here, right? It should be, then if you want, it's going to be E to the theta WT plus theta times T if you want. Okay. So here, right, if you want to convert it to W, then you would do E of, right, indicator function of, let me continue down here, right? It will be, so here will be equal to E of the indicator function of WT less than or equal to, sorry, WT plus theta T. Sorry. I convert to E, so I need to multiply with ZT. Okay. Then I convert W tilde to W. Is it okay? But the point is, actually notice a probability statement on the tilde side is no longer a probability statement, or at least not a directly, right? A probability calculation, right? Probability exactly. You understand? Because you have the ZT here. You cannot convert it to a pure probability question. But doesn't matter, right? Because you just take expectation anyway. But the point is, you see, to convert a probability statement here, you will convert to an expectation statement on the on the old side, physical side. Any question on this? This is important. You will need to do homework on this. So if there's any question you want to ask now on any step. Is this okay? All right, I'll take that as a yes. So notice, right? Notice that. So the point I want to convince you is to establish, right? The whole glorious Gaussianov's theorem says that this is a p tilde Brownian motion. And you see, it just does all the work for you, because you see, if you really want to check that something is a Brownian motion, I challenge you. So that's frankly speaking my question, right? Even knowing all the pieces of the information, like even if knowing that Gaussianov theorem tells you so, unless you trust it with faith, meaning you don't check it, if you really want to go and check it, you see that calculation itself is definitely non-trivial. Okay. Nevertheless, right, this is the point that we want to check this, right? This is part of the class. Well, after all, it's a math class. So we want to deal with this in a more detail. In other words, we want to verify Gaussianov, all right, as much as we can. So all these things I was telling you lead to this following observation. We want a more compatible characterization of a Brownian motion. Okay. In other words, right, the whole thing that Cherry was reading, right, zero, normal increments and independent increments are very good. You should always remember that. But that's not very convenient to work with in this framework, in this change of measure. We want something else. And something else actually is also similar to what Cherry was saying. It has to do with exponential structure. Okay. So the following is a lemma or whatever, you know, just a small result that says WT is a p Brownian motion if and only if e to the sigma minus 1/2 sigma squared t plus sigma WT is a p martingale for any sigma. Okay. You understand what this is saying? It is a very nice statement, okay? Basically, it says that, right, to check that something is a Brownian motion, you do not need to go through the whole normal derivation thing, right? The normal justification, like normal distribution. All you need to do is, roughly speaking, take expectation. You need to take conditional expectation actually, but in other words, right? You need to establish that for any s less than t, expectation of e to minus 1/2 sigma squared t plus sigma WT conditional Fs is equal to this. If you can do this, then if this is true, then you can conclude that WT is a Brownian motion. Okay. Now, is this surprising? First of all, right? There's even a question of why is this even true? In other words, right, how is this equivalent to what Sherry was reading? In other words, W0 equal to 0, W has normal distribution, W has independent increment. How does this translate to that? Okay. Any idea why? So if WT, right, is a Brownian motion, then right, it's clear that this is true, right? We have done this calculation before, actually. Sorry, there's no expectation here. I apologize. No expectation, just this. Okay. This should be easy. You have done this calculation on homework. Is this direction? That is what we're trying to say now. How to do that? So first of all, right, notice something like this. That if you choose t equal to 0, right? If t equal to 0, what does it say? And s equal to 0, what does it say? It says that, right? And by the way, if t is equal to 0, the convention is t equal to 0, then W0 is a constant, okay? We always start at a constant, and then after that, we start to be random. So if you do that, right, e to the minus 1/2 sigma squared times 0, right, plus sigma times W0, right, should be equal to what? Should be equal to, hold on, let me see here. Oh, sorry. I think here it doesn't have to start at 0. Scratch that. Sorry. This doesn't say that it have to start at 0. It just started somewhere. Apologize. It doesn't say anything like that. Maybe W0 equal to 0 is built into the structure. Sorry. That doesn't work. Let me scratch that. Okay. The reason is I think this structure right here does not say anything about W value at 0. The martingale structure doesn't say that. But let's address the other one. For example, right, WT minus WS has a normal 0T minus S, right? Random distribution. Why is that true? Well, it comes from here. It comes from here, right? You go backward, so it comes from here. So for example, right, if you, because WS, right, is known by FS. If you flip it back, you get expectation of e to the sigma WT minus WS, right? Condition on Fs is equal to e to the minus 1/2 sigma squared T minus S. Okay. Right? I bring the WS over here, and I bring this over here. So notice several things, right? When you take conditional expectation, you expect that, right, it's going to be a function of WS on this side. But the fact, right, that there's no WS here, right, no WS on the right-hand side, means that WT minus WS is independent of the information generated by S. Okay, because when you take conditional expectation, there's nothing that shows up. So therefore, right, that means that you are not dependent on this in any way, because you condition on this information is like you don't condition. All right. So that's exactly the piece of independent increment that we just talked about. What about this piece? So then that means that you can drop this, right? That means you can drop this. What does this tell you? What does this tell you in as far as like a probability statement? What does this information tell you? Well, so you see that, right? This is a random variable. This is just like, you know, a free constant. So if you have something like this, suppose you have a random variable such that e to a tx is e to a minus 1/2 t squared, right? E to a minus 1/2 t squared sigma squared rather. What can you conclude about x? This is true for any t, right? This is true for any t. What can you conclude about x?
Normal.
Exactly, right? This is exactly the moment gen function of the normal. So x is normal 0 sigma. So here, right, I guess the role of sigma and t got changed, right? But this is sigma right here that plays a role of t. This is sigma squared right here. So in other words, right, this tells you that wt minus ws has normal 0 t minus s. Okay, which kind of complete the Brownian motion, right, characterization, except that, you know, I just realized that this doesn't say anything about where the Brownian motion starts. But that actually is immaterial because, you know, of all Brownian motion characterization, right, where it starts is the most artificial one. Because if you have a Brownian motion path, right, you see like this. It starts at 0, right? That's convention. This is WT. But if you start exactly one above it, right? I mean, for all, I mean, you don't call this like a standard Brownian motion, but it's still Brownian motion, right? Because everything WT does, it does, just in parallel way, right? So in that sense, I guess here, you may call it like, you know, if you subtract the starting point, right? So I guess, or I can throw in the definition that W0 equal to 0 in here. So I don't have to worry about it. It's part of the assumption, right? But what I want to say is, right, this martingale characterization is important because it established two facts: the independence increment and also the distribution of the increment at the same time by the moment gen function. And yes, right, it connects deeply with what Cherry was talking about in terms of the exponential structure. Okay, any question? So how does this connect back, okay, to our Gasanov? So connect back to Gasanov. Gasanov says, right, that remember ZT is e to the minus 1/2 theta squared t plus theta, right, WT. The change of measure kernel says expectation tilde of x is expectation of ZT times x. The claim is W tilde t is a P tilde Brownian motion. Okay. The proof is what? The proof is, right, you need to establish, right, by our lemma. So notice that actually, right, oh, sorry, right, so what is W tilde T? W tilde T equals to WT plus theta T, right? Theta times T, right, is a Brownian motion, right? So first note, right, that W tilde 0 is equal to 0 by definition, because, right, when you plug in 0 here, you get 0. Then by our lemma, what we need to show is that e to the sigma W tilde, right, T, sorry, yeah, minus 1/2 sigma squared times T is a P tilde martingale. Okay. What does that mean? What that means is that you need to establish that expectation under tilde, all right? So for t less than big T, expectation under tilde of e to a sigma W tilde big T minus 1/2 sigma square big T condition on small t gives you e to sigma W tilde small t minus 1/2 sigma square small t. Okay. All right. But then how in the world can you do this, right? Why is this any easier than the other one? Is easier than the other one because of this following another lemma, okay? So there's a conditional change of measure lemma that says this, right? Remember that we say, right, if x, right, is a random variable in the biggest sigma algebra. So if you want to take expectation of x under the new measure, you just do z big T times x. Well, what if you don't want to take expectation? You want to take conditional expectation. What do you do? Right? That's exactly is the question here, right? I don't want to take expectation, right? This is in FT, but I want to take conditional expectation. What do I do? The answer is this. Oh, is easy. You take expectation like this, condition, but that's not all. You also have to divide it by conditional expectation, like this. Is that okay? So what it does, right? What this lemma tells you is that you can take conditional expectation under a new probability. How? By taking conditional expectation under the old probability, right? Don't forget the change of kernel, but that's not enough. You have to divide by conditional expectation of the kernel as well. Then you will get this. Any question? All right. So applying this lemma, right, to this calculation, I claim that you can obtain the result. All right, I claim that you can obtain the result. So I won't do it further for you. I'll leave it for homework and review session so you can explore it. Okay, but that's the gist of the problem. Going from using this lemma and using, right, the martingale structure, you will be able to verify that that's the case. Any question on the idea of how these pieces fit together? Are we okay? The key is to change the symbol, all right? To keep track of the symbol. Do not get confused between the tilde and the non-tilde, and know how to change from the non-tilde to the tilde, right? For example, to change from expectation conditional, right, to the non-tilde version, you need this. But then W is also W tilde. So to change to W, you need to add theta T, right? For example, don't forget that kind of stuff. If you keep all these pieces straight, it will fall into your lap, I guarantee. All right. No question? All right. So, all right. So to demonstrate to you why, right, this is useful, right, or like application of this change of measure, okay? You'll see something like this. First of all, right, the standard Black-Scholes model is mu, right, sig STDT plus sigma STDWT, right? And you want to convert it to DST equals to R STDT plus sigma STDW tilde T. Now, let me quote another theorem that you should have seen before in Professor Larson's class called fundamental theorem of asset pricing. Which actually has to do with the no arbitrage thing that Cherry was quoting, right? It says a market is complete and arbitrage free. I wonder if it's called perfect or something, I forgot. If and only if a risk neutral probability exists and is unique. Okay, I'm not sure if it complete also means arbitrage free or not, but I think maybe I'm wrong. If those of you remember the notation, the keyword more precisely, you can correct me. So first of all, what do we mean by a complete market? Did anyone hear about this term? Do you remember what this term means? Is it a new term? So by complete, right? Maybe I'm wrong here, but it means every derivative can be replicated by the underlying. And the money market. Is this the term that was used, or am I mistaken here? So every product is hedgeable. Every product can be replicated, right? That's what we mean by a complete market, I think. Right. And arbitrage free means that you cannot have an opportunity to make money without risk. Okay. And so those complicated, right, financial technical condition can be translated to verifying a risk measure. Probability exists and is unique. So that's the beauty of it. The beauty of it is the fundamental theorem of asset pricing allows you to translate something that is potentially complex financially to something that is just simple in terms of mathematics of the model. Okay. So the question is, in this classical Black-Scholes model here, does a risk neutral probability exist? Is it unique? Or in other words, right, is our model complete and arbitrage free? Is it? Well, so the answer here is yes, by Gasanov, right? You see that this is where the mathematical rigor comes in, that it tells you that because Gasanov gives you an explicit change of measure kernel that you can use. So yes, right, that as long as you have that theta, right, by using that theta to be the Sharpe ratio, you can change the measure. So yes, it exists. Is it unique? Yes. Why? Also by Gasanov, because there's only one choice of theta, namely this. There's only one choice of theta. Okay. So in other words, right, Gasanov theorem is what allows us to conclude that our model is arbitrage-free and complete. Any question? To show you, right, what could go beyond this framework, right? Variation, right, of Black-Scholes model. For example, you could have something like this. dst is mu st dt plus sigma 1 stdw1t plus sigma 2 stdw2t. Okay. Is this allowed? You bet it's allowed, right? Why? Because all I'm saying is I'm having two sources of noise. I'm having two sources of noise, okay? Where W1 and W2 are independent Brownian motions. Okay? So in other words, right, and this is actually a more realistic model than the previous one, in the sense that, right, remember, we say a source of noise can come from, action of trading and that kind of thing. But if you think of the source of noise as like, the sector or some peculiar thing that depends on the stock, then, a stock may be in a crossroad of many things, right? It may be a member of S&P, which drives it into having like, having some source of noise. It may also be some other kind of stock, maybe, S&P, but maybe a little bit into the technology or something, or the finance, I don't know, right? That will give it another, right, kind of noise. And by the way, right, I just say these are independent to make it easy for you. This can be correlated, all right? So the fact that you're in S&P and you're in the finance sector doesn't mean that you're independent. So there can be a correlation too. But they don't have to be the same Brownian motion, the same source of noise, okay? So notice that this model, right, does not change fundamentally at all how the return looks. Okay, why? Because the return still has rate mu, right? The percentage return still has rate mu. The variance of the return changes though, right? Because before the variance, right, or the volatility is sigma, right? What is the volatility in this case now? What is the volatility in this new model? What is the volatility in this new model? Are we all burned out already? It will be sigma 1 square plus sigma 2 square square root. Do you agree? Right, because it's is the variance of the return divided by t, I guess, or divided by dt, right? So the variance of the return here is sigma 1 squared plus sigma 2 squared times dt, because the variance of both of these is dt. So therefore, right, it's a standard deviation, right? So it's going to be square root of that. Okay. So you see, right, it's exactly like the previous model. I just called this sigma before, but now it's this term. So of course, so right, I mean, but this doesn't, the percentage return is still normal, okay, with this mean and this standard deviation or the variance. So I can play a lot around this model. For example, what is its risk neutral version? What is its risk neutral version? What is its risk neutral version? Well, I don't know much, but I know that to be risk neutral, it must have rate return R, right? And so that means that I would have some new Brownian motion under my, under my P tilde, right? Where W1 and W2, W tilde 1 and W tilde 2 are P tilde Brownian motion. So this is just what I want, okay? Now the fundamental theorem of asset pricing comes in and say, question, right? Does a risk neutral probability exist? Is it unique? Okay. So how do we answer this kind of question? How do we answer this kind of question? Well, to answer this kind of question, right, you have to, again, connect back between this model and this model, right? You have to connect back between this model and this model. So in other words, right, basically, if you review this model under the framework of W tilde, you will see that it's going to be, right, let's say mu, let's divide by ST, right? It's going to be mu dt, okay? And sorry, I want R dt, right? If I want R dt, then I want sigma 1, right? It's going to be something like dw1t plus theta 1. Some change of drift. And then I need sigma 2 dw2, right? Where what must happen? What must happen is that somehow, right? Somehow, this put back together should give me this, right? In other words, where, right, R plus sigma 1 times theta 1 plus sigma 2 times theta 2 is equal to mu. Is it okay? What are the known and the unknowns? The known, right, or the given are the R, sigma 1, sigma 2, and mu. The unknowns are the theta 1 and theta 2. Okay. So that's what we need to solve for, right? How many choices of theta 1 and theta 2 can we have? How many choices of theta 1 and theta 2 can we have?
One.
One? No, infinitely many. Right? Because you have only one equation here with two unknowns. You have infinitely many choices of theta 1 and theta 2. And again, right, this is where Gasanov comes in. Gasanov tells you that for each choice of theta 1, theta 2, you can make this into a W tilde prime motion. Is it okay? That's what Gasanov does. Gasanov tells you that with each choice of theta 1, theta 2, you can change it to a different, to a P tilde prime motion. Well, so the question of does a risk neutral probability exist in this model? The answer is absolutely yes. Is it unique? The answer is no. Because for each theta 1, theta 2, I get a different change of measure kernel. So the answer is no. All right. And again, it's all because of Gasanov. You see, you can chase all this back to Gasanov and how Gasanov tells you how the measure is constructed. Okay, so I'll stop here. But let me tell you, right, this has very realistic like kind of implication where basically it tells you, right, what does it mean here? Risk neutral probability exists means there's no arbitrage. Well, fine, we can do pricing here. But the fact that it's not unique means that there will be some product that's not replicable by the stock alone. So philosophically, what happened? What happened is you have too many sources of noise and you only have one asset to trade, okay? The trader would probably call it something like, you know, you have too many sources of risk and you cannot hedge it with so many few products, okay? So the philosophy here is the number of products must be at least equal to the number of source of noise before you can hedge away all the risk. Risk here actually, right, is caused by source of noise. So okay, we will, I will give you problems, right? And we will, on review session and homework, and we will illuminate this more in the next class. All right. Okay, thanks for attending, guys. If you have any questions, as usual, I will try to explain. If not, see you next week.
All right. Thank you, Professor.
Yeah, thank you. Any question about homework? Anything you want to ask? All good?
I have a question about just like, I guess not really the homework, but just kind of trying to make sense of like one of the homework questions.
Yeah.
So like just in general, for I know how when we represent the Greeks, we can use differential equations. Not differential, like the derivatives, sorry.
Yeah.
We can use the derivatives. But then like, I don't know, when I try to make sense of it financially, it's kind of counterintuitive for me. Like, so like I had to follow the equation to be able to answer like some of the questions on the homework, but I'm just trying to make sense of like, you know, for the butterfly spread.
Yeah, I think that's the point too. And actually, let me show you something, right, which I plan to get to today, but obviously I could not, which
Okay.
is, let me see here, which is something that all of you should look at and try to understand, which is how, for example,
Oh yeah, I looked at this.
the
I think
Greeks, right, can
yeah.
change with the stock or with the its own, right? And these shapes are fascinating. And I think this is a routine question on interview on how to explain this shape, right? But this is a shape for a call option. And so what I was asking you is a butterfly, but yeah, right? Mathematically, we can all easily draw this, but financially, right? They care for you to explain what's the intuition behind this shape and stuff. Yeah, I know it's not easy, but yeah, go ahead. So what's your question?
So like I did exactly like not exactly this, but I found the like on a resource the shape of the graphs for the Greeks.
Yeah.
And like I think the only one I really have trouble understanding is the delta graph for the butterfly spread. So it looks like a sine wave from like 0.
So first of all, right, I want to clarify something here. I'm not asking you to graph the delta of a butterfly,
Yeah.
right? But it looks like a sine curve. I did not try it, so
Oh, no, sorry. It's just like I looked at another resource. It might not be particular to the parameters, but I feel like it should still agree. It's just like one period of a sine curve. So it's like 0 where the in between, like the strike 2, and then it's positive, like the half a period of a sine curve
Yeah.
when it's less than that strike, and then it's negative when it's greater than that price.
Uh-huh.
I understand it being 0 because of the
Payoff
shape,
is 0.
the payoff, and it's like it's a peak, I guess.
Right.
Like that was kind of my explanation. But when I think about it, like shouldn't it be negative? Like just looking at the payoff graph, because I think the way I look at it is that you're at the maximum payoff, so you would only go down. So as the stock price changes, your position would, like whether or not it goes up or down because you're at that peak, it will go down no matter what. And then I got confused because that was contradicting to what.
So right, it's a very good question, right? And we want to think about it a little bit. For example, right? I mean, when you look at the delta of a call option, right?
Yeah.
You could argue, I'm not sure if you could argue also there's a peak, like you said, somewhere, right? But the fact is the delta of call option is clear, it's always positive, right?
Yeah.
So again, I don't know, right? Of course, a spread is a more complicated product, right, than the call option to begin with. But what I want to say, right, and by the way, I'm no expert on this. I just asked you the math. But I think, right, think about it. The fact that you're above the peak doesn't mean you cannot make more money. Because when we say, right, when we say the stock price change a little bit, right, because the stock swing, remember, this is a random stock movement, right? Yes, the stock goes, right, but it depends on where it moves. If it moves backward, don't you get closer to the peak? Right, when you say the stock price change, okay, fine, sorry, fine. How to say this? If the stock price change a little bit, right? Again, my intuition may be that it still can make money, right? Because it can swing in the right direction for you. You understand what I'm saying? So yeah, it's random, right? The nature of the stock price is it changes random. It can go in both directions, right? So when you say that something is negative, right, that means that the option price definitely will decrease, right? A stock price increase, right?
Yeah.
That could be too. I agree with you. It's perplexing, but I was thinking that, huh? So you're saying the delta of a butterfly never gets negative. The delta of the butterfly never gets negative.
Oh, no, it gets negative as long as the stock price is above the middle strike price.
Yeah. Okay. So that makes sense. So sorry, what was your question then?
Okay, so like from the shape of the payoff, I think it's very clear the values when you measure the derivative, because truthfully it is like upward sloping, so that makes sense.
Yeah.
And when that the delta would be positive near that upward slope, and then it's negative for that downward slope.
Uh-huh.
I just have trouble understanding because like my intuition is that when you're at that middle like strike price, like the delta is equal to 0. But I feel that from that point, like your payoff can only go downhill because you're at the max. So
No, okay, so hold on, right? Let's put it in context. This is K1, K2, K3, right?
Yeah.
Okay, so this is a butterfly, right?
Yeah, exactly.
And so this is payoff. And when you look at the delta, right? You say that, I assume you say it looks like this.
Yeah, it pretty much looks like that.
Okay, and I think it makes sense, and you say it doesn't because
I'm confused about the
I
K.
guess we were talking about here, right?
Yeah, we were talking about, I'm confused at this, like, because at t0, t equals to 0, we're at that k2 point because that's what s0 happens to be.
Yeah.
But if we look at the payoff, I'm at the very
Oh, no,
top.
so this is the graph of delta versus what, right? I think this is a graph of delta versus S, right? I assume that's what
Yeah.
you're doing. So when you do here, when you graph over here, that means your starting stock price is around here compared to the stock price over here, right? That's what you're saying, isn't it? That's the meaning of the graph.
I'm confused.
No, so basically, right, delta here, when you do this, you're graphing delta as a function of S.
Yeah.
So be very careful when here you are saying the S not change, right? The S0 changes. So S0 is no longer always at K2, right? In fact, if this is a graph that you got, then at K2, the graph is 0, I guess, right? But if you start, basically, if you have an option, right? If you have the butterfly spread, where you are starting, right, the initial stock price somewhere here, then the graph tells you that your delta is being negative. In other words, if your stock price increase, then your option will go down in price. But if your stock price decrease, then your option will go up in price, which seems to make sense.
Yeah, that part makes sense to me. Is it okay if I like annotate on?
You want to share a screen or something? I mean,
Oh no, I think I can like edit it like right here
Oh,
compared to like right
oh,
here.
awesome! Wow,
This is
perfect.
the one that like
Yes.
gets me because
Oh, you don't see why it should be 0 there? Is that what you're asking?
like I see because it's flat, like this is like a peak, but also I think like this payoff, no matter if you go left or right, like this is S as well, no matter if you go left or right, the payoff goes down. So I think
I
like
see.
no matter
Okay.
how it makes
Right,
sense.
right. Oh, so mathematically, you see, you wonder why is 0 there rather than negative, right? Because you wonder why is 0 here, right?
Yeah.
Interesting. No, you're right. You're right. I see what you're saying. So first of all, right, are we sure numerically this is 0 or just by looking at graph? Because somehow the eye can be deceiving, you know? Sometimes it maybe a little bit. Are you sure? So did you print out the delta at this point and you get a 0?
No, I didn't get exactly 0, but I got like 0.003 something.
Oh, so very close to 0 then.
Yeah.
Huh. But you're right, right? Theoretically speaking, if you go to this way, the option price goes down. If you go up to this way, the option price goes down. Oh, you know what, Sherry?
Yeah.
It could be an inflection point, right? You know, like,
Okay.
you know what I mean? Like, actually, what you're asking, if I'm not mistaken,
Oh, sorry.
is something like this, right? If we have a graph like this, the derivative here is 0, right?
Yeah.
Oh, you know what? No. I know exactly your mistake. Your mistake is you're thinking calculus wrong. In this sense, the sign of the derivative is always taken with the right movement.
Wait, sorry, what?
The sign of the derivative is always taken with the right movement. Move to the right.
Yeah, so this is positive, like this part is positive and this one
No,
is
so what it means is if you move to the right here is negative. But yeah, exactly. This part is actually positive because you're going up. So you should look at it like that. So positive, negative, so that's why it's 0.
Oh.
You're right, it decreased on both sides, but the decrease on the left side means a stock decrease. So 2 decreases make it positive, right? So no, your graph is perfectly correct. It's your interpretation that's wrong, right?
Yeah, I think my interpretation, because like it was very, okay, I see.
Oh, I got taken by you for a while too. I was thinking, yeah, you're right. But just think of the classical calculus. It makes sense, right?
Okay, yeah, that makes sense then.
Yeah.
Thank you. Yeah, okay, thank you so much.
Any other question?
That's all on my end. Oh, I also just wanted to ask, like for the iron condor spread,
Yeah.
I got a positive rho.
Okay.
And I'm just trying to also make sense of it because I'm not sure if it should be positive or
Rho
negative.
is one of the harder thing. I regret asking rho. I think I meant something else. Rho is change with interest rate. Actually, to be frank, I'm not sure many people care about rho. Let me tell you, right? Most quantity people care about are the gamma, the delta, sorry, delta, right, and gamma, and vega.
Oh, I see.
Um, so if you really want to, prepare for interview or whatever, I think pay attention to those three first. Rho, I don't know. I throw it in because it's Greek, but I should not, in the sense that it's a movement with interest rate. No, actually, people do care because, say, for example, if the Fed, right, raise a interest rate or decrease interest rate, it will affect, So they do care. But right now, the interest rate curve is very flat. No movement there, I think. But yeah, do ask. Again, I just want to qualify. I may not offer you anything too insightful here. But
It,
what do you find role to be?
it's like it wasn't even like we don't have to explain our row, but I just want to clarify because like I kind of want to make sense of it.
Yeah.
So like for the butterfly spread, I feel like it was a lot easier because to make sense of it because it's all made of calls. But then once we like combine calls and puts into the iron condor spread,
Yeah.
I get kind of like it mixes up with like what I think those like if the Greek should be positive or negative. And then so for row, I got like almost 5, so 4.8 something. And then so I'm just thinking that if the stock price is lower, uh, if the stock price is lower, then that means an increase in interest rate is beneficial. But I can't really see the
Wait,
connection.
so what graph are we talking about? We graph row with respect to what?
I'm just thinking and with respect to
F.
V, uh, what is F? Sorry. The
S,
P.
S stock. Or row with respect to what?
I'm thinking of oh yeah, the stock and row would yeah, that works too.
So did you graph it or no?
I didn't graph this one because this one was too hard for me to find resources on.
Oh, okay. No, I'm just asking. So if you want to discuss a behavior, right, you want to tell me what graph
Oh,
versus which, right? I think for me, row versus S is interesting, but maybe row versus R is also interesting.
okay. Yeah, I think I was thinking of the actual like definition for this one instead because I couldn't find a graph. I was thinking of like how it basically the definition I wrote down row measures the interest rate sensitivity to
Yep.
option positions.
Yep.
I was actually just thinking about like the correlation between interest rate and option position. So like the price or payoff. And then I couldn't make sense of it because I can't really
No,
envision.
I understand. And the only thing I can comment, right, on you is actually my ignorance, meaning I don't even recall the graph of the row for a call option. Do you know how it looks for call
Oh,
option?
for the call one, I had a research, but I didn't write it down.
Okay, but how does it look roughly, right?
Um,
So I would say that to understand everything, right, we want to go back to the call option first because I think that's the easiest one, right?
okay.
And after we see the behavior of this, right, then we can extrapolate. For example, that's why I want to show the class the graph of that. I guess you guys have seen it anyway. But the point is that, right, I think understanding the intuition of the call option first, and then right extrapolate to this. But what I want to say is that, right, rho, I feel like it's probably awkward to interpret too, because the movement of interest rate is a play in the bond market and money market, right? How it affects your stock is a little bit subtle because I think maybe what's behind the scene is like people might have more interest, right, to devote to so money market becomes more expensive, right? Rho basically or R is the price of the money market, right? If R becomes, higher, that means the market access is more expensive. So in that sense, like, somehow, like when you think of like replicating your portfolio, it takes more money to replicate in a cash position. That will in turn have an effect on your, option price. That's all I can say, right? How that plays out, right? I am not so sure. If I see the graph, maybe I can tell some BS story on it. but like, no, I admit it's not easy. But definitely, right? I mean, look into it if you want to, discuss after you look at it. We definitely can, kind of meet during office hours or something. But without having thought about this, I would say that all I tell you right now will be BS, like not anything deep, anything, kind of like.
I actually just
subset.
realized, like, upon talking to you, that I can just test it using the code to like adjust
That's
bar.
the beauty of the code, right? That's
Yeah.
exactly it. You have customized tool here, at least to graph it correctly for yourself, right? Make sure you graph it correctly. I graphed this and I made so many mistakes, right? Graph it, make sure you graph it correctly. And then B, from the graph, try to see if you can read the behavior. It's very good training. I tell you this because, again, right, the Greeks people care deeply about, because they have to balance, right, a portfolio according to the Greeks. And then after that, right, is a routine, I think, not routine is too much, but is a popular interview question on, okay, tell me the meaning of the delta. What do you think the delta of the call option? What range is it? Where is it maximum? Why you think, that kind of thing, or maybe the gamma, what I mean? And there they want you to give an intuition on why, not the numerical value, right? And so these are good training if you want to kind of, prepare for that side of the interview, I would say.
Okay, I see. Yeah.
But
Thank you so much.
having said that, right, I'm ashamed to say that I don't have much to offer besides I can look at with you and try to make sense of it with you, but that's not my area of expertise, right? I have done a little bit, so I can see a little bit, but not more than that.
And it helped because like I was really like I had the exact opposite idea of what it's supposed to be initially, and that really bothered me because like I know my thinking was wrong, but now like I kind of see where the flaw was.
Sure. So yeah, definitely play with it and then let me know if you want to discuss any particular.
Okay. Yeah.
Yeah.
Thank you so much.
Yeah.
Thank you. Bye.
Bye. Any other question from anyone? Homework question? Any questions? No other question. Oh yeah, happy Lunar New Year. Yes, go out and enjoy. Still do your homework though, but yeah, go out and enjoy.
I have a question, but not for this course. Because right now I have an opportunity to have a RA position in another course.
Yeah.
So because I'm